sign for the third lecture, because I've seen that many people signed everything, and they should have done it, so these 6 people are fantastic. In the spirit of Nicolò, they get a beer, because that's exactly what you should do, right? So you shouldn't sign in advance. So please, let's circulate among these people. Please.
Okay. Good. I hope that you know, the digestion of the lunch is going to be okay even during this. Thought this would a good moment to stop and, let's say, do a few exercises in the sense of simple examples like this, because maybe some of you have never solved this kind of equation, so they for them maybe it's not obvious what I'm speaking about. I'm just keeping this for future reference. So as a conceptual recap of all this thing is this. So so the whole idea is that we have some system and environment, and there's some total Hamiltonian, and from the unitary dynamics of the full state, with a specific initial condition, we are going to do this 3 approximation, Born, Markov, and rotating wave approximation to get Lindblad, which is an equation that's just, well, I can say more, which is a linear and linear ordinary differential equation for the state of the system alone. We just went through these 2 approximations, and for these approximations, we essentially need that the coupling constant between system and environment times the correlation time of the bath must be small. And this is equivalent to say that the typical dissipative timescale of the dynamics induced by the perturbation is much longer than the correlation time of the bath. So the bath is a very fast, has a very fast dynamics in comparison. So the Born approximation gives you an equation which is an integral differential equation that involves only rho s, whereas the Markov approximation is a way of getting rid of the integral kernels and getting an equation which is time local, and so usually called Markovian in this sense. This equation is not yet Lindblad, but it shares many many features with that. It's called Redfield master equation. So I think that the first step, the last step, I'm going to do it tomorrow, but let's say for now it's not an extremely severe issue. I just wanted to give you a glimpse of, you know, how this machinery works in practice. Essentially, as long as we're dealing with two-level systems, the RWA is not really important. So, first of all, how does a solution to the Lindblad equation look like? Which is actually very similar to Redfield. So, the Lindblad-Master equation, or also this one, will look essentially like this. The rate of change of the density matrix is given by the application of a linear operator on the density matrix itself at the same time. This linear operator is basically this old stuff. It's actually a super operator, if you wish, in this jargon, because it's an operator that acts on operators, because rho itself is an operator. But let's say conceptually, it's a linear operator on a specific vector space. Now, what is the solution of a linear equation? How do you solve this? Well, you just need to diagonalize the operator. It means that there is a certain set of operators which are eigenstates of this linear operator, and so let's say if this was an Hamiltonian, this would be the eigenvector of the Hamiltonian. This is not an Hamiltonian in the sense that essentially, if you write this down if you choose a basis for the Hilbert space and you write this down, you will find that this operator is not Hermitian. So in general, has two sets of eigenvectors, which are operators, though, and has complex eigenvalues. Okay, this is a little bit of a technicality, but let's say the idea is you can always diagonalize it like this, and then the solution to this will look like this. So by the way, these are called right eigenvectors, and these are left eigenvectors, because you can think of this as acting on L on the left. Again, nomenclature. The main point here is that whatever the form of this linear operator is, the solution is a bunch of exponentials. This term contains, so these L operators contain the information on the initial conditions. These R operators are the objects that give the physical state, and these lambdas are rates. Now, these rates are generally complex, so they have a real and an imaginary component, so that essentially these guys are describing damped oscillations in general. Now, and you may see the risk that if one of these rates, of course there would be some mu, if one of these rates were to become negative, these exponentials will blow up in time. And this is exactly what can happen if you use Redfield. So if you take this one, there is no guarantee that the rates have all positive. These eigenvalues have a negative real part, which means these eigenvalues may blow up in time instead of going to 0. No, I mean, yes, I probably should use a different notation. Well, I mean, they are related, but they're not necessarily the same, depending on the system. For the simplest cases, they're actually the same. Yes. So the whole thing that I was telling you at the beginning about Lindblad is the fact that if this operator has the Lindblad form, then you can mathematically prove that these rates are all positive, so this stuff goes to 0. Or at best, they might be 0, so you just get oscillations. And actually, you can prove something stronger, which is that always exist one rate which is 0, so that the corresponding state, the corresponding right eigenstate, is a stationary state of the dynamics. So if you put all of these together, if you have an operator in Lindblad form, you can, the dynamics which is being described is that of a state which is relaxing exponentially to a stationary state. This, by the way, includes even unitary dynamics as a limiting case. In unitary dynamics, these rows are essentially projectors of this kind, where these are the eigenstates of the Hamiltonian. And then the lambdas are all purely imaginary. You just guess oscillations. Or, of course, they can be 0. If all the projectors in this form are stationary states in unitary dynamics. If you initialize the system in an eigenstate, it will remain there forever. So let's say this is the idea for finite dimensional systems. The dynamics is just Markovian dynamics is just a bunch of exponential functions. If you have reason to take the thermodynamic limit, so infinite dimensional systems, that you could have some surprises. In essentially is like doing a Fourier transform. If you put many oscillating factors, you can basically approximate any function. So, but you need a continuous. You need to transform the sum into an integral for doing so. I will not try to do this in these lectures. Okay. Let's take, for instance, this example. So this is very generic. But let's take this example, which is more concrete. We have a two-level system. I'm using quantum optics notation, so ground and excited states, which map to down and up. The Hamiltonian can be written as sigma z times the level spacing. I'm assuming that the bath is a bunch of oscillators. This is a very common assumption. And then we have this coupling in which this is the A operator, and this object is what I call B in the coupling. So, as I was telling you, so the first step is to compute these eigenoperators, which are the basic ingredients that we need. And in this case, which means simply in this case, computing the time evolution of the A operator under the system Hamiltonian, so without interactions, without anything, and singling out the exponential factors and reading the corresponding eigen operators. I don't know if you've ever seen this kind of stuff. It's not particularly difficult to prove this equation. You just use the commutation relations for spins. And depending on your taste, I mean, either you go through like, you take the commutator of this with this, you're going to get sigma y, and then you take another commutator. Or you take your quantum mechanics book, and you'll find this as the SU2 algebra of matrices, and this is exactly the equation that tells you that the sigma plus and minus are the eigenoperators for this object. And if you wish, I was telling you at some point that in a system with a non-degenerate spectrum like this, the eigenoperators have essentially this shape. Indeed, if you write them explicitly, they are exactly like this. So sigma minus is the operator that projects you from the excited to the ground state. Sigma plus is doing the reverse. Let's see. Would you like to try and derive that one from this one in as an anticipated tutorial? I don't know. If you wish, otherwise I will go on. You would like? Let's take. Before I make, there should be a dagger here. Would you like some more time? Or, I don't know, I guess to complete everything, it takes a little, if it's the first time you do it, it takes a little bit of effort. Omega square over 4. I don't know where are you taking this from. At this level, I mean, you should consider these as certain coefficients that we need to compute, but they are related to these gammas. The small gammas here are essentially these objects. Okay, no, I just realized the mistake I've made. This alpha is not that alpha, my bad. These are modes, I don't know, momentum modes, call it as you wish. I see. Yes. Otherwise, you don't get really a bath. You get another, it's impossible to have Markovianity there. There is no, this is endless. Which notation? Are they discrete? It can be really kappa. I don't. Why not? Why not? So this is just a rewriting of this, which has a form which is more suggestive. So we start getting a commutator, and then there's this sandwich term. There's a dagger here, and there's the anti-commutator. In this case, there is no alpha, there is no beta, because it's just one operator coupled to one operator. So for now, you can, at this level, you can just forget about the bath. You just assume that, I mean, you need to compute a correlation function, take the Laplace transform, and this will do it in a minute. But let's say the structure of the equation at this level is more important than the actual value of the coefficients. So if you put everything together, we have this was one eigenoperator, which is sigma minus, and its complex emission conjugate sigma plus, and you just need to plug these, treating these as just some coefficients that we can compute. And let's say if tonight you sit down with a beer and work out the details, you will essentially find this, except for, let's say, there's notational point. So if you rewrite this equation in this form, you will find, okay, that the coefficients, big capital gammas, occur in these two specific combinations. So if you divide them in a real and an imaginary part, the real part is what enters here and will give you the relaxation rate, and the imaginary part is going to give you a term which is actually in this form, and it's basically a renormalization of the frequency of the two-level atom. It's called the Lamb shift. It's there. Sometimes it's important. In this specific example, is usually not particularly important, because essentially you can think, well, if I'm going to measure this system in reality, the frequency I measure is already including the Lamb shift. So whether, unless your intent is really computing the Lamb shift with respect to the bare parameter, in a sense, the case of the hydrogen is famous, is the Lamb shift. But then usually to make that computation, you need to resort to quantum molecular dynamics. I mean, again, it's usually not the most important component. These small gammas are the dissipation rates, and those are usually more interesting. So, again, as an example, so the final result is going to be an equation in this form. I'm going to tell you what are these coefficients in a few minutes, but for now, I think maybe it could be nice to see how to solve that equation, and I mean, as an example of dissipative dynamics. Now, this is a two-level system, so the density matrix is a 2x2 matrix, and we can simply take its matrix element on a specific basis, and that the eigenbasis of the Hamiltonian is usually the most convenient one, because essentially everything here is already adapted to that basis. So, I take the diagonal matrix element on the excited state. Okay. If you take this, the expectation value of this object is 0, because well, in general, it would be something like there is a frequency difference simply because you have the Hamiltonian, and these are the eigenstates of the Hamiltonian, but of course the diagonal element is 0. And this is what we expect. If we didn't have any dissipation, the population of the eigenstates of the Hamiltonian cannot change in time. Those are stationary states. So we just start with this. For instance, this term, sigma minus, so let me write it down. By this definition, sigma minus is just projecting on the ground state. This is just the dagger of this, so it's another ground state. And, well, and then you can, yes. And then instead, this guy will give you 0, because this is a projector on the ground state, essentially. So by the same token, for instance, well, let me write it down explicitly. Sigma minus plus rho yes. So, for instance, this object here, this is 0, because this is you cannot excite the two-level atom twice. So this is 0. And by the same token, this is also 0. Is it? Or am I writing bullshit? Yes. No. Yes. Then, I mean, you can play the same game. No, 0. What am I writing? excited, excited. Excited. And this is ground, which means against E. Yes, it's E again. Yes, sorry. This sounds really odd. Why? And it's E again. Yes, yes, yes. No, you're correct. It's E again. It's E again. Yes, it's should be 0. Should be. I mean, I guess this doesn't change it, but this is very odd. Plus or minus. Minus. This is ground state. No, okay, then this. No, okay, well, should work anyways. No, it's not 0. You're correct. Then this bit works similarly. So okay, now this term here will give you 0 if you're projecting on the excited state. Because again, sigma plus acting on excited state is going to be 0. So we just get the anti-commutator and okay. So this is E minus plus, okay. And this no, wait. No, okay. Yes, now this should get 0 again. Yes, so this object is 0. This should be, or not? Sigma minus on the excited gives you ground state. No. This one. Yes, it should be 0 indeed. Okay. Because the output is G and minus no, this should be finite because this is E. This is essentially a classical rate equation. So you get that the excited state is decaying, but it receives contribution from the ground state, which instead is excited, is promoted to up with a certain rate, gamma p. And there are no off-diagonal elements here, which is actually a feature of the Lindblad master equation. Now you can have fun in deriving this object. This time, this object has an Hamiltonian contribution. The difference in energy between the two states. And then it also gets contributions from the anti-commutators. And again, this, so when one is working in the eigenbasis of the Hamiltonian, the diagonal elements of the density matrix are called populations, because they give you the population of the states, and these guys are the coherences, because essentially they appear whenever you have superpositions in the state. And in Lindblad dynamics, populations and coherences evolve independently. Again, this is a feature of Lindblad dynamics, which is partially an approximation. In the full Redfield equation, this is no longer true. We only need two equations for this, because the other coherence is just a complex conjugate of this, because of the matrix is emission. And then conservation of trace is telling you that the sum of the diagonal elements is 1 at all times. So, should I erase something? Probably. So, the evolution of the coherences is not particularly difficult to compute. It's oscillation. Yes, it's oscillation with the frequency of the system plus decay, and of course the two sources of decay. Let's say both the pump and the loss processes contribute with the same sign to the decay, and then instead the excited state has this dynamics. Yes. So, as I promised you at the beginning, the dynamics we get is just a bunch of exponentials. These are purely decaying. Here you also have oscillations, but just exponentials. And here you can see the emergence of a stationary state, because this guy and this guy goes to 0. So at very late times, the coherences decay completely. And you get a certain population. Now, one thing that we will see in a few minutes is that if the environment is initially at thermal equilibrium, then these two coefficients have a specific relation. This you might know this as a fluctuation dissipation relation, or Kubo-Martin-Schwinger conditions. Yes? No. That's the condition for this dynamics to be positive semi-definite. I'm assuming that already I did the full, let's say, Markov approximation, so I'm just taking the asymptotic coefficients. Unless you want to do stuff at very early times, this is usually the case. Yeah, if you wish, a more correct dynamics would be with time-dependent coefficients, but then this is less nicer. Strictly speaking, that's no longer Markovian dynamics. It's weakly Markovian because the system has a notion of absolute time. But yeah, it will work nevertheless. So if you use this relation, you can write this. Yes. Like this. And this is nothing but it's the population of a thermal state. So this is how an example of how the Lindblad dynamics done properly brings the system to the temperature of the bath, of course, assuming that the bath is initially in a thermal state. If the bath is not in a thermal state, then this could be anything. And you generally need to keep a time dependence of the coefficients also. Okay. All of this is more or less clear. Now, if you wish, you can, I don't know, try different jump operators without worrying too much about the dynamics. You can take a jump operator which is sigma x or a jump operator which is sigma z and play the same game. And you find which kind of dynamics you have. Since, indeed, I was mentioning this before, maybe I can give you a glimpse, unless it's an exercise you want to do right now. No, taking the, so this is an example in which, okay, you do all the Lindblad stuff and you get thermalization. You can be more simple-minded and just choose jump operators which are Hermitian and see what happens. So the two options at this one, and this one. You can essentially play the same game, writing down, taking matrix element of this object, and then see it where it brings you. I don't know if you wish to do that. Otherwise, I can just point out as the most significant point at the blackboard. What? The second one, I mean, the point is, it will work. It will give you a dynamic, some kind of dynamics. But I already did you a spoiler that this dynamics is unphysical unless you have a bath at infinite temperature, of course. let's say, whenever, I don't know, would you like to do this exercise to convince yourself? Otherwise, I'll try to convince you in a shorter manner. Yes? Yes.
Something different in the meantime. So is it easy to generalize if my my S Hamiltonian is just some band structure in a solid? So so like if it's not like an n-level system, but my jump operators have momentum transfer, is that straightforward, or becomes this a mess?
No, you can do that.
Okay.
The problem,
Like I don't know if I shined like light on a semiconductor or something.
Yeah, it becomes a little bit of a minefield, depending on what you want to do. So in principle, there's nothing preventing you from, taking, I don't know, your coupling to phonons, which will give you jump operators, which probably look like the Fourier transform, the Fourier components of the density operator for the fermions. And the jump operator will enact some momentum transfer. Now, the problem there is that you have a very small level spacing. So in principle, if you have the system which, if the bath is inducing transition, which have neighboring momenta, so they have arbitrarily close energy in the thermodynamic limit, then it becomes really hard to justify these approximations.
Why?
So we're going to see having very small frequencies may tamper with the Markov approximation, and it will definitely tamper with the rotating wave approximation. I haven't told you yet this stuff, but I'm going to show you in the next lectures. That kind of example is an example that I will do in the rotating wave approximation part, if I manage to arrive at it, of course. So what you should find in these two examples, so in the first example, you get what is you could call pure dephasing. So it's a dynamics that does not touch the population, because of course you can diagonalize. I mean, the jump operators are acting in the same basis as have the same eigenvalues as the Hamiltonian. They commute, and then you just erase exponentially the coherences. So in a way, this kind of dynamics is not even injecting energy in the system, because the energy only depends on the diagonal, because we are measuring energy on the diagonal, which is sigma z. Instead, these dynamics will bring you inevitably to a state of infinite temperature. In general, whenever you have jump operators which are emission, the infinite temperature state is always a solution. Of course, for instance, also here, if these two are equal, then you get to an infinite temperature state in principle, but you start also with an infinite temperature state. Instead here, whatever is the initial state, you're gonna just end up in an infinite temperature state. And so the difference, this difference also entails a different applicability with actual physical systems. So this one can actually be obtained from this derivation simply with a coupling which is like that one, but with an A operator, which is sigma z. So you have sigma z times maybe that sum of displacement operators. And in this case, sigma z is also a constant of motion. Its evolution is given by itself. So this means that it is also the eigenoperator. But this is, as I was saying, if omega equals to 0 is an option for the dynamics, then the corresponding eigenoperator is a constant of motion. And the only constant of motion here is the Hamiltonian itself. Now this one, it's highly non-generic. If you take sigma z, you're gonna get sigma z, but if you take sigma x, like there, you don't get sigma x, you get sigma plus and sigma minus. And the same if you take sigma y. This, you cannot expect this from this derivation. Either, if not, let's say, as an extreme limit of this solution, when you put an infinite temperature, so beta equals to 0, these two guys become equal, and then you get this is 1/2. But that's, again, a limit. And this equation corresponds, unless you have reason to approximate your bath as an infinite temperature bath. I don't know if you've ever seen one. But this, for instance, would rather correspond to a dynamics that is made of measurements. So you're measuring the spin of the particle, let's say, along x, and you're averaging over the results. And then the dynamics will be exactly given by this without any approximation. Because measurements span, measurement outcomes are all the eigenstates of the measurement operator, of the observable you're measuring, which span the whole Hilbert space. So when you average, in the end, you get the identity, because you will visit every state in the Hilbert space with equal probability. And this also means, of course, if you do projective measurements, you're gonna heat up the system on average up to infinite state. But then again, this is physical because, measurement implies a sort of driving in the system, whereas this does not require any driving, and indeed is not injecting energy in the system. That one is injecting or subtracting energy of the system depending on the initial state, but the outcome is guaranteed to be thermal, so you don't violate thermodynamics. Okay. So these are very simple examples, but I guess instructive because they tell you, look, we've seen, okay, how it works somehow thermalization, and the issue of hermitianity of jump operators. Many people use Hermitian jump operators as a phenomenological choice when you want to describe a kind of evolution which is just erasing coherence from the system and giving you a thermal state. But again, if the outcome is infinite temperature, then you might question whether this dynamics can go on for arbitrarily long time in an actual experiment. Most likely that this dynamics can be just an approximate one, unless you're doing measurements, of course. Okay. Okay. Another thing that can be said at this level, which is also very important and often neglected, is that the eigenoperators, so the jump operators that you have when following this procedure, they depend crucially on the Hamiltonian. If you change the Hamiltonian, you're supposed to change the jump operators. For instance, if I have this, okay, we have all made the derivation, and you will have that this generates jump operators which are sigma plus and sigma minus. But now, suppose that I add a perturbation, which is like this. Let's say an external field along x, I couple at the Hamiltonian level, I couple a little bit this level. Which are the jump operators which I should use? Many people maybe would naively think, well, it's going to be sigma plus and sigma minus because I'm just pumping and losing energy to and from the bath. But if you think a little bit, this cannot be because, you know, like for instance, if the environment is at 0 temperature, you would like the system to thermalize to the ground state. But now, sigma minus will try to bring the system into the ground state of sigma z. But if you have this object, then the actual ground state of the system will have a small component along the excited state. This object is not going to be the exact ground state. So if you keep the same jump operators here, which I erased, but there was this term and this term. These guys will bring you to the wrong stationary state. And this, okay, this could have been an exercise, but maybe for another day, or you can do it at home and tell me tomorrow if there's something that doesn't match. But let's say if you, okay, let me take this. Now, if you take this new Hamiltonian and you compute the thermal expectation value, where is that? Yes. So you compute this thermal expectation value over the new Hamiltonian. You will find this, which is essentially slightly bigger than -1, which, sorry, this is also a 0 temperature, which is easier. So at 0 temperature, this is the only terms that remain. Whereas if you keep these jump operators and you still compute everything as if they were correct, you will get a different object. Which is not, this, if you perturb the Hamiltonian and use the old jump operators, you'll converge to the wrong state. And you can also see a qualitatively why. Now, what I told you is this thing. If the bath is initially at equilibrium, then it will equilibrate to the Gibbs ensemble, but this is just the unperturbed Hamiltonian of the system. There is no dependence on the interaction. This is an approximation, if you wish. It's a lowest level approximation to get corrections due to the interaction to that object. You need to basically have a master equation that goes beyond second order. So here, this is second order perturbation theory. So the rates are that you predict are second order in perturbation theory, basically Fermi-Golden rule. And the final state is actually correct to the 0th order. But again, this is thermodynamics. If you have reason to neglect the interaction between the system and its environment, the thermal state does not depend on interaction as a first approximation. So this object cannot contain gamma. But this object contains gamma. And this is going to be a typical thing when you use the wrong jump operators. The true jump operators are the ones that map, project a state on the true eigenstates of the system, which you can compute and have fun. But that's the idea. So this thing is, it's a thing that's often neglected because, you see a certain dynamics is still exponential, you never violate positivity, so it seems that everything is doing fine, but depending on, of course, what you want to prove, again, if you have an environment which is thermal, the system must thermalize, unless the system has a special dynamics which prevents thermalization. But this is never the case for a few-level system like these ones. And the linear master equation is essentially was conceived and designed for these finite dimensional systems in which you don't expect anything bizarre to happen. So I guess as another, well, the last comment on eigenoperators and jump operators is going to be about multipartite systems. So all of this is very simple and nice because it's just a single system, but you could have two spins which might be interacting, or maybe many, and this brings about a new set of complications. So this could be an example, and you can even, let's wait. Okay. You can have an autonomous like this, but even with 2 is sufficient. This is some kind of dissipative easing model, but I mean, two spins would be sufficient. Now the alpha index here is going to be a position. It's which subsystem is being acted upon. So these are the A's. So the gammas also might have a structure in real space depending on the shape of these objects. But let's say the important point is that, again, the procedure is take the system Hamiltonian, diagonalize it, and then compute the appropriate, let's say, J E M minus En, which is something like N sigma J what the? It's going to be something like this, or maybe summed over more eigenvalues in case you have degeneracies. So I'm not going to do it explicitly. There are various options. You can, take 2 spins with a coupling and have fun. The main point I want to take is, so the eigenoperators are essentially projectors on the systems on the exact eigenstates of the system. Now, if the parts of the system are interacting, in general, you would expect their eigenstates to have support on each part of the system. So you cannot expect the eigenvalues of these the eigenstates of these objects to be factorized in the single site. So this object, so these jump operators, the eigenoperators, and then the jump operators, are not going to be local, which is a thing that I think for many people comes as a surprise, especially if you have a background in solid state or condensed matter, in which all the interactions are local, and so on. But in this case, you always expect that that the jump operators are going to act on all subsystems at the same time. And again, this is a requirement for thermalization, because it's the jump operators must know the true eigenstates of the system. Otherwise, it's going to be impossible to bring an initial state to the correct thermal state. And if the eigenstates are spread upon the parts of within the parts of the system, the same will be true for the jump operators. I don't know, you can have fun. You can take this 2-side sizing model and diagonalize it, or maybe a Heisenberg model also with this, and try out the various eigenstates, and you will find that you will generally never obtain local objects, which are either you're going to have, I don't know, terms like this, maybe, or at best something, let's say, operators that are summed over the sites. If let's say this can be annoying, especially if you're doing exact dynamics, it means that the complexity of the dissipative part increases to write down and to implement. But this is the price that you pay for thermalization. There are efforts to, let's say, make these operators more local. You can exploit Lib-Robinson bounds and have quasi-local approximations. But let's say there are people, especially in quantum thermodynamics, that are very concerned by this kind of stuff. Generally, if you truncate these objects to local operators, there is always a finite chance that you will gonna violate thermodynamics, meaning you start, decreasing entropy and not thermalizing. So this is a word of caution. It can be a reasonable approximation. If, for instance, your system is, I don't know, a Hubbard model at a very large interaction, then the eigenstates are essentially localized in space. And so using local jump operators is not a big deal. But of course, you cannot expect to go into the metallic phase with delocalized eigenstates and have local jump operators that brings you to a thermal state. It will never happen, in a sense. It's highly non-generic. So I think this more or less concludes what I wanted to tell you today. Tomorrow, we're going to see more on the Markov part, look at stuff in frequency, and finally, RWA. Questions? Again, shock. So, did you know that the Lindblad master equation gives you always a thermal state? Yes, you know, maybe. A few people seem. No, in like this. I mean, never mind this. But have you ever encountered this statement before? That the thermal state is an exact solution of the Lindblad master equation, generically speaking, of course. Repeat.
Which means the diagonal terms are always like numbers, stationary, and the rest of them decays with the time, right? The off-diagonal terms.
Yes, but not only. I mean, I'm saying that this is a solution of the master equation.
Oh, okay.
A specific form, of course, not which is generally, I mean, in the basis of the Hamiltonian, this is diagonal, of course.
Okay. When the time is going thermodynamic limit, okay.
I mean, if it is weakly coupled, then only it gives the thermal equation. I'm not sure actually.
Repeat, sorry?
If it only weakly coupled, then it will give the thermal equation, or in general case.
I think that is his question, I think.
I mean, all of this is based on weak coupling.
Yeah,
Yeah,
exactly.
but if you have
coupling is
strong coupling, will
stronger.
you have also the Gibbs
Yeah,
state?
that's my question.
Well, I would say, okay. The point, okay, if the system is strongly coupled to the environment, then it makes less sense to divide the universe in system and environment. And then the question becomes more, does the system plus environment system obeys the eigenstate thermalization hypothesis, so that if you take a small part of it will look like thermal, because then that's the question. And generally the thermal state might receive corrections from the interaction, but this is not what this equation is meant for. I mean, I would say it's a conceptually related but distinct scenario.